Good afternoon, everyone, and welcome to the third lecture series of Physics Colloquium of this season. And we are very happy to basically convey to you that today's speaker is quite well-known particle physicist. And, I again request everyone in the audience, please switch off your video because I keep on repeating, please switch off your video and mute your mic. So he didn't need much introduction at this point of time, but for our young student, I would like to mention few words about him. That he finished his PhD from University of Calcutta in 1994, and then after doing couple of postdocs in SINP, TIFR, and so on, he joined the IIT Kanpur as an assistant professor in 2000, and then he remained there until 2007. And since 2008, he has been serving Tata Institute of Fundamental Research as a professor, and his main research interest lies in electroweak interaction, supersymmetry, and extra space dimension. So, as I mentioned to you, apart from the very well-known particle physicist, he is also quite well known to deliver some of the popular lecture, and we have been witness such kind of lectures during our student days in IIT Kanpur. So that's why we were very interested to have him a speaker for our colloquium. So today he will be talking about again one of the great researcher of Indian from the Indian soil, and he will be delivering a lecture on the life of S.N. Bose, and the main tagline is a forgotten hero. So with this, I basically hand over the forum to Professor Raychaudhuri, and again invite him to deliver the physics colloquium today.
Yes. Okay, thank you, Pankaj. Thank you, Pankaj, for that very nice introduction. Slightly hyping my abilities, but nevertheless, I will try to do some justice to what you have said. And I'd like to express my gratitude to you, Pankaj, and to Shubhaditya, who had the original idea, and to IIT Guwahati in general. I would have loved to say it's a pleasure to be back in Guwahati to be giving this talk. Circumstances don't permit it, but it's good to be giving the talk to you all, and to be able to convey the life of one of India's greatest sons. So let me share the screen now. So is my screen visible now?
Yes.
Okay, so it's visible?
It's visible.
Yes, okay, thank you. So let me start. So my talk is about Satyendra Nath Bose, and as you can see that I have taken the title, A Forgotten Hero. I have copied a very well-known film by Shyam Benegal, which is called Bose, The Forgotten Hero, and that is of course a different Bose, and but nevertheless, of course, another famous one. Now, those of you who are wondering why I have this symbol in the middle, why these colors in the middle, that's not because this talk is sponsored by Pepsi, but that is a simulation of a Bose-Einstein condensate. And this is one of the most exciting consequences of the work of S.N. Bose, though not his direct work. And here is the man himself. So, Bose at the time when he sort of made his famous discovery. But let me begin the story by putting everything in the right context. So, this is the title of a famous book by George Gamow, 30 Years That Shook Physics. And these 30 years are the years from 1900 till about 1930. And during these years, quantum theory and quantum mechanics, the entire quantum revolution happened, and it changed the way forever how we think about nature and about the physical world. And here are the people who made it possible. And so all the greats are here, from Einstein and Bohr at the top, and all the way down to Fermi and Gamow himself and Wigner and Landau and so on. But if you look at this picture, you will see that there is one face which stands out among all the rest. And you can see that all the others are Europeans, they are Caucasian, white skin, whatever you wish to call it. And one person is completely different. He comes from a different race, different color, and from a different part of the world. And this is the person who we are going to talk about today. So every good story should start with once upon a time. So let me also begin with once upon a time. And we go back to the middle of the 18th century and to a German optician called Joseph von Fraunhofer. Now, Fraunhofer was an optician and he was able to invent the spectroscope. So you see the spectroscope here in the middle. There's a person peeping through it. He's peeping at the sun, which he should not be doing. But anyway, people were not so careful in those days. Now, what happens that when you look at the sun through a spectroscope, let's see, you look at the sun, which as we know is a sort of yellow disk in the sky, you see a spectrum, of course, the famous spectrum of the 7 colors of Newton. But if you look carefully at a high resolution, then you will see that there are these black lines in the middle. And these lines were discovered by Fraunhofer and they are known as the Fraunhofer lines. The interesting thing discovered by Fraunhofer was that if you look at the sun, not in the usual time, but during a solar eclipse, the spectrum gets reversed. Whatever were the bright lines, I'll just show it again. The dark lines become bright lines and the bright parts become dark. So let's focus, for example, on this. Let's focus on this one, this dark line here. And you see that when it becomes dark, this becomes a bright line. This, in fact, is the sodium line, which we come to. But this thing remained a curiosity and a mystery for about half a century. It was understood only half a century later with the work of Robert Bunsen and Gustav Kirchhoff. So what they found is that many of the lines of the Fraunhofer spectrum match with the line spectra of the elements. Now, why did this have to wait for 50 years? Very simple. That is because no one had invented a nice hot burner which would vaporize the salts. And it was Bunsen who invented this humble device, which is now there in every chemistry lab, the Bunsen burner. And using this, they were able to vaporize many of the elements and look at the spectra. And when they did that, they found that it matched with the line spectra of the elements. And then Kirchhoff took it ahead and proved using thermodynamics, which he was an expert at, that the spectra or the distribution of energy from absorption and emission will follow the same pattern. And this is expressed in the Kirchhoff law, which says that the emissivity and absorptivity form a constant. The ratio is the same for all different bodies. So if you choose a body whose absorptivity is 1, in other words, it absorbs everything which falls on it, so that makes it a black body, because nothing comes out of it. Only things come out of it, nothing, it absorbs all things of it. Doesn't reflect anything. So therefore, of course, this 1 you don't need to write in the denominator. So let's remove it. So this is Kirchhoff's law. For a given temperature, the emissivity and absorptivity are proportional. So now, of course, you need to know what happens with temperature. And the challenge was to find this function of how the energy is distributed over wavelengths for different temperatures, which is known as the black body spectrum. And this, of course, has to be found from experiments. So these experiments were actually performed by these two gentlemen, Otto Lumer and Ernst Ringsein. And this is of course, this is not their graph, this is a modern graph. But you see that there is this kind of a peaked graph. As you go to higher wavelengths, the emissivity falls off, and at very low wavelengths also it falls off. It's peaked somewhere in the middle, and where the peak is also depends on the temperature. So as the temperature rises, the peak moves towards lower wavelengths. And this is the wavelength range of visible light. Beyond that, we have the lower wavelengths, higher wavelengths, which are infrared. and the lower wavelengths, which are in the ultraviolet region. Now, of course, when you have something like this, you demand a theoretical explanation. So the first theoretical explanation was devised by a gentleman called Wilhelm Wien. But Wien's theory worked nicely for small wavelengths, but when you went to higher wavelengths, then it started deviating from the actual curve. So the 7000 Kelvin curve, if you follow Wien's theory, would work very nicely for the first part of the curve, and then near the peak and so on, it would start deviating badly. Now, Wien's idea was was sort of a combination of empiricism and theory, but a very nice theoretical model was created by these two gentlemen, Lord Rayleigh and Sir James Jeans. But lo and behold, their theory worked very nicely at the other end of the spectrum for large wavelengths or small frequencies. And then as you went to low frequencies, it deviated. And in fact, when you went down to very low frequencies, very low wavelengths, very large frequencies, then the thing just became infinite. And which was that time known as the ultraviolet catastrophe. But as you went to the ultraviolet end, it just gave you an infinite answer, which had no meaning because the total energy emitted by a black body is finite. So here we had this problem. We had two theories, one working at low wavelengths, one working at high wavelengths, and nobody understood how to put them together. Clearly, both were wrong. But in fact, the Rayleigh-Jeans model was actually based on very simple and very clear reasoning. And therefore, the failure of this formula gave a big jolt to classical physics around the turn of the 20th century. So let me explain why. Well, Kirchhoff, in proving his famous law, had shown that the radiation which is confined inside a cavity. So imagine a cavity like this, which has perfectly reflecting walls, and the radiation will keep bouncing off. So if a radiation comes in, it will keep bouncing around inside, it cannot come out. So in that sense, it will absorb the radiation. And if some radiation, once it comes to equilibrium, then of course, because of Kirchhoff's law, it will go out as a blackbody spectrum. So the radiation confined inside a cavity is the same spectrum as the radiation emitted by a blackbody. Now, Boltzmann, using this idea, had proved that the radiation emitted by a blackbody per unit area is proportional to the fourth power of the temperature. And that is correct because that had already been discovered by Stefan. So you see Boltzmann on the left side and Stefan on the right. So Stefan had already empirically discovered that this radiation emitted is proportional to T to the 4. So that showed that this idea of a cavity is sort of the right idea. And what the Rayleigh-Jeans formula did was simply to count the number of degrees of freedom of this cavity radiation and give each of them the same energy and see what you get. So Rayleigh had actually done that counting. The number of vibration modes of a standing wave inside a cavity between a frequency nu and a frequency nu plus d nu is given by the Rayleigh number, 4 pi nu squared by c cubed, where c is the velocity of light. Of course, radiation is electromagnetic radiation, so it moves at the velocity of light. But there is something missing in this. And later, when James Jeans joined him in this, they added a factor of 2 because, after all, this is electromagnetic radiation, so it is transverse. So there are two transverse polarization modes of light. So there was this factor of 2. And then to that, they added the classical equipartition theorem of energy, which was proved by Boltzmann, that each mode gets an equal amount of energy, kT, where k is the Boltzmann constant. And therefore, you simply take this number, the Rayleigh count, multiplied by 2 for the polarization, thanks to Jeans, and kT from Boltzmann, and you get this formula. 8 pi kT k nu squared t. And now you see here that as nu becomes very large, this thing also becomes very large. This, in fact, is the Rayleigh-Jeans formula. So you can hardly have something simpler. And obviously it's wrong because it gives you an infinite amount of energy. It's clear that if you integrate over all values of nu, then you will get nu squared d nu integrated, which will give you nu cubed. And nu cubed, of course, when you go from 0 to infinity, is infinity. So there is something seriously wrong here. But what can be wrong? the calculation is very simple. It's very straightforward. So that's the question. Now, one possibility, of course, the wave theory of light, on which the basing of this counting of the standing wave mode was done, is no longer in doubt. It was no longer in doubt at Rayleigh time. It's no longer in doubt now, because of course you can see interference patterns. This is an interference pattern from a laser, which many of you have probably done in the laboratory. But in all kinds of interference patterns, Newton's rings and so on, were already well known. And then the counting of standing wave modes is simple. I'm sure you have done that in high school, at least for sound and windpipes and so on. And that's a very straightforward calculation. And again, that polarization is an everyday phenomenon. You see here a Polaroid lens, and you probably possess them. They're probably sitting inside your camera or even in your phone. So polarization is also an everyday. There's no doubt about these. So there's a mystery. What's going wrong? So when you have a mystery, it's good to call in a detective. And who better than the most famous detective of all time, Sherlock Holmes? He had said that it is an old maxim of mine that when you have excluded the impossible, whatever remains, however improbable, must be the truth. So what is left? Polarization is fine. The wave nature is fine. So therefore, it has to be the equipartition theorem. So therefore, clearly, the equipartition theorem has to be changed. But how? How can we change that? Let's go over the logic for the equipartition theorem. Let's assume that the amount of energy which can go into any of these vibration modes is arbitrary. You can put more energy into one mode, into less. You know that already, because that's how you get overtones, that's how you get light of different colors and so on. Now, the probability for the energy going into any mode is given by the well-known Boltzmann factor. That's the statistics. So it is e to the minus energy over kT. All right, so let's try to calculate the average energy. So the average energy you calculate by taking the energy, weighting it with this probability factor and integrating over all energies, divide out by the total probability. So take the value of NE and substitute this Boltzmann factor here. Now it's simple to do these two integrals. If you do them, the top integral comes out to be kT whole squared. The bottom integral is just kT, and therefore the ratio is kT. This is what Boltzmann had done. And you can't think of something simpler. But of course, this is the classical equipartition theorem. This is what Rayleigh and Jeans had used, and this is wrong. So it's a big puzzle here. Well, a solution was thought up in 1900 by Max Planck, and basically he made a guess which turned out to be an inspired guess. So he asked the question, what if we don't do an integral, but we do a sum? What if the energy values, instead of being continuous, as I assumed when doing the integral, suppose there are multiples, integral multiples of some standard value. So let's call that value E naught, and n times E naught will give an energy packet En, and n is some integer. So it's 1 E naught, 2 E naught, 3 E naught, and so on. What would happen if we did that? Then, of course, this is the same formula as I showed you in the previous page. You take the energy, multiply by this probability, and go ahead with the integration. So now, instead of the integration, you will take En, the same En, multiply by the corresponding probability, which is given by e to the minus En over kT. And substitute n E naught for En everywhere. Now, fine, go ahead and do these sums. You can use the ordinary infinite series sums. And what you will get is the following. The upper one sums to this object. The lower one sums to this object. One factor like this cancels. And you are left with this factor. E naught divided by something like this. So this is clearly different from just kT. This is a different equipartition law, which you get by just assuming that the energy values have discrete values rather than the continuous values. So that's the new kind of equipartition theory. Now, if you look at this formula, so this is the same formula I have here. this one, and I've just translated it here. And suppose the values of E naught become very small. So then you can expand this exponential. It becomes 1 plus E naught. The 1 cancels, and now you can see the E naught also cancels. The KT goes to the numerator, and you're back with Boltzmann's result. This is the Rayleigh jeans result. And of course, that is what you would expect, because as E naught goes to 0, you will be going towards the continuum limit. Now, Planck had this inspired idea that since small E naught corresponds to the classical result, it must occur whenever the Rayleigh jeans law works. And where does that work? It is for small frequencies. Okay, large wavelengths, small frequencies. So when the frequency is small, then E naught must be small, which means that at least to the first approximation, E naught must be proportional to the frequency. So you can write that as E naught equals to h nu, where h is a constant. And today, this is called Planck's law, and the constant is called Planck's constant. Okay, now just a little curiosity. Why is it called H rather than P? It should be P for Planck rather than H. The reason is that Planck himself called it H, and H at that time stood for the word Hilfgröße, which means extra constant or useless constant, Bekar constant, Faltu constant, because he didn't take this thing very seriously. But the H symbol has stuck. Well, now taking E naught as h nu, this same average energy formula which I have here, I just replace the E naught by h nu, and I have this h nu here and h nu here. And now this is my new equipartition theorem for electromagnetic radiation. So let's rework the Rayleigh jeans formula using this. The blackbody spectrum would be first the Rayleigh factor, counting of modes, the factor of 2 for the polarizations, and this new equipartition law. So if you put them all together, you get this one. You get this law with a nu cubed and h nu factor minus k by kt minus 1 factor. And this is known as the Planck's distribution formula. The nice thing about this is, of course, we expect it to match the Rayleigh jeans formula for low frequencies, because this is going to reduce. Remember, this part is already there in the Rayleigh jeans formula, and this part is going to reduce to the equipartition, classical equipartition, and therefore we would get back this factor. So it will reduce to the Rayleigh jeans formula, but what is interesting is that for high frequencies, it reduces to the Wien formula. So it does precisely that combination of the two formula. And it turns out that it matches both the qualitative and quantitative features of the observed blackbody spectrum. For example, if you integrate this overall energy, you get something proportional to T to the power 4. And in fact, the agreement with the experimental data of Lummer and Pringsheim was simply too good to be a coincidence. Look at this graph here. This is actually taken from the paper of Lummer and Pringsheim. And they have put these, I think these are probably related to the melting points of different, or the incandescent points of different elements. But you see the dots, and the dots almost fall exactly on this black line. They are such a good result that I'm afraid that if a student produces this in the laboratory and takes it to the teacher will be suspicious and say, bring your raw data and let me see what you have done. So it's a fantastic match. And such a fantastic match cannot be just a coincidence. But if we accept that this is the correct theory, then we must accept that energy values, instead of being continuous, must be integral multiples of an energy packet. Now, but what is the sense in talking about the energy of a wave being tied up in packets? I mean, a wave is a wave. It's a sort of continuous thing. How can the energy come as packets? That's a very strange idea. Well, Planck thought he had an explanation. The explanation was the following. So you take this cavity of Kirchhoff and assume that there are some oscillators in the walls of this cavity. And these oscillators, when they emit the energy, they emit them only as packets. So an oscillator in the wall can emit only E0, 2E0, 3E0. It cannot emit anything in between. It cannot emit 1.2 E0, for example. But once the waves have come out into the cavity, then they all merge and form these continuous standing wave patterns, which is why when you actually look at the energy, you will get a continuum of energies. But when it's being formed, then it has this. So the analogy is like this. Imagine a tap, and actually what happens, you have droplets of water coming out from a tap. So these are discrete. They come out as 1 drop, 2 drops, 3 drops, and so on. But when you have a large number of them, it doesn't look like that anymore. It just looks like a continuous stream. But actually that continuous stream is built up of so many drops of water. So Planck's idea was something like this. Okay, he didn't have an absolutely crystal clear theory, but he felt some phenomenon like this must be happening. Alas, his theory lasted only 5 years, because Planck's best friend, I don't have to tell you who he was, killed the idea within 5 years. And how did he do that? With his theory of the photoelectric effect. And here is a cartoon of that. What happens in the photoelectric effect? The light falls on a material where there are electrons, and some of the electrons are knocked out of the metal or the material. And when they are knocked out, it turns out that they absorb integral multiples, which absolutely follow the Planck law. And that's why you get this Einstein equation for the photoelectric effect. This is the energy of the photon. Some of it goes into the kinetic energy. Some of it goes into overcoming the work function. But now that means that the energy is also absorbed in packets, and it doesn't mix up in the middle. Now let's take an analogy with which you are all familiar nowadays. Suppose you've ordered something from, let us say, Amazon or Flipkart or some, and in their packing center, they have made a packet for you, with all the cardboard and the sellotape and so on. And now they have sent it by a courier to you. And when you get it, you get the same packet. That tells you that on the way, the courier has not tampered with the packet. The courier has not taken all the packets, mixed up all the stuff into one, and then again, before giving it to you, separated them out into packets. No, that's a very unlikely thing to happen. It's simpler that the courier just transported them as the same packets which they had been given, and that's what happens. For radiation, it's the same. If it's being emitted as packets and absorbed as packets, then it must be packets in between. Moreover, you could also ask that once the radiation is emitted, then at the moment just before it meets some other material for the photoelectric effect, just before that, how is it going to know that the next moment it's going to meet a material and therefore it now has to separate itself into packets? That can't happen. It will violate causality. So therefore, it's clear that the energy is always remaining as packets. Now, this idea was not liked by most people. So Robert Milliken, the famous American experimentalist, he found the idea so repulsive. Sorry, there's a bit of noise. Okay, so maybe that's Milliken's ghost. He found the idea so repulsive that he set up a beautiful experiment whose whole purpose was to show that Einstein's photoelectric equation was wrong. So what he planned to do is to measure this, take the frequency of the light and measure the kinetic energy of everything and show that they are not proportional. Okay, and this was his result. So on the left side, he plotted what is called the stopping potential, which is equivalent to the kinetic energy of the electron coming out, and the frequency on this side. And lo and behold, it's perfectly proportional. Once again, the points fall almost exactly on this straight line. And in fact, today, if you look at a textbook of quantum theory, this is the experimental proof given that Einstein was right. So Millikan, who set out to prove Einstein was wrong, ended up by providing the best proof that Einstein was right. And so Einstein had the last laugh. He got the Nobel Prize for having found the theory of the photoelectric effect. And Millikan, for having been proved to be wrong, was also given a compensation. He also won the Nobel Prize for having experimentally proved the theory of the photoelectric effect. So that's a lesson that sometimes you set out to do something and often you get something completely different. But nevertheless, you get all the credit for it. In 1923, which was about 7 years after Millikan's experiment, Arthur Compton found that these energy packets, which by then had been named photons, they can scatter off electrons and cause the electrons to recoil. Now, why do things recoil? They recoil because of the conservation of momentum. And therefore, this means that these energy packets are also carrying momentum. Now, what is it that carries both energy and momentum? If something does that, we call it a particle. And so there must be particles of light. But this is what Isaac Newton had told us 400 years ago. But nevertheless, that idea had been thrown out because we had found all these wave properties. So now the energy packets will be carrying momentum and energy, and there must be particles. We have seen that. So what's going on? It was a big puzzle at that point. And therefore, people thought that let's not think of them as particles, but let's somehow get around and arrive at Planck's law by some other means. So, of course, this is Planck, who originally founded by the thing I have told you, but not thinking too deeply about it. This is how Planck looked at 1900. He was, of course, younger then and looked like the military officer he had been before that. The next person, about 10 years later, was Peter Debye, and he used the ideas of probability, first person to use the ideas of probability to derive the energy transfer from the cavity to radiation. Remember, they were still thinking in terms of oscillators in the walls. The Planck's idea was still there. And then came this particularly brilliant idea from Nathanson in 1911, who showed that Planck's law tacitly assumes the photons to be indistinguishable. And really, this was also something which was used by Bose and which we understand today better using quantum mechanics. But in 1911, Nathanson had this idea. And so if anyone is more forgotten a hero than Bose, then it is Nathanson. So, but he didn't make the discovery. Nobody took it seriously. Well, Ehrenfest and Camerlingons, you've heard the name. Camerlingon is, of course, discoverer of superconductivity. They pointed out that Einstein's photons and Planck's distinguishable light quanta can't be the same. There has to be some difference. And that caused a lot of confusion in 1914. So then Einstein, he couldn't take it up in 1914 because he was busy setting up the general theory of relativity. But when he had finished that in 1916, he came back to this Planck's oscillators, and he combined Bohr's theory, which had then come in 1913, with Planck's oscillators, and that's the very famous theory of AB coefficients, which you learn in the undergraduate classes. It doesn't really apply to the cavity radiation, but it does apply to high intensity radiation, which is why you needed to understand lasers. But that would come, of course, many years in the future. Then once the theory of Planck and this idea of collisions between photons and electrons had come in, the young Pauli in 1923, he showed that you could get the Planck's law by looking at collisions of Maxwellian electrons. Maxwellian means having the Maxwell distribution, which had a nonlinear interaction with the photons. So therefore, the interaction would have not just this A rho term, but also a B and rho prime, where rho prime is the density of the electrons. So there is a problem in this because, of course, the photon would have to know what is the density of the electron before interacting with the electron. So this could only be an effective theory. But it was some kind of derivation. And then Einstein and Ehrenfest took this further. Instead of electrons, they replaced them by Bohr atoms interacting with photons. So in 1923, this was the state of the art in this subject. A fair amount of confusion, various derivations, none of them quite correct. And the reason was that all of them were assuming the classical statistics of Boltzmann. So with Boltzmann statistics, you have to do something, put in these extra assumptions, none of which are completely correct, except for very high intensities, which was not what was achieved there. The solution, in fact, came from a quite different part of the world. And it's sort of amazing when you look at the world map and you think of the world as it was then. So all of these developments were happening in Europe, on the continent, mostly in Germany, in Holland, and so on, and Denmark, and not elsewhere in the world. Okay, of course, Milliken's experiment happened on this side of the Atlantic. But the solution came, sorry, I'll come back to this. The solution came, the solution came from this spot here, far away from Dhaka. And I think even now, if you ask people in Europe, where is Dhaka, many of them will not know where it is. At that time, perhaps they would know even less. So now we'll come to the person who made this theory. And first I'll have to discuss the making of SN Bose. What was the milieu in which created this person and which made him able to do this kind of work. So we'll go back. And now I'll take you across the country to Kolkata. And here is a Google map of Kolkata. You see the great river Hooghly here and the Maidan. And we take you to this part of northern Calcutta. And here to this spot, which is a region called Gua Bagan. And here is a close-up. And you see here, it's a very congested area, old congested area, lots of small houses, lots of brick houses. And here is the Gua Bagan Park. So this whole area is Gua Bagan. And here is the famous Scottish Church Collegiate School. This is the major arterial road leading to the north. And here there is a road called Ishwar Mill Lane. So as you see, it's completely a residential area. Ishwar Mill has disappeared long ago, but the name survives. And here is a house. And it was on this house, and you see one of Kolkata's iconic rickshaws. And there, of course, in this particular house, it's still well maintained by Bose's family. So Satyendra Nath Bose was born on the 1st of January 1894 at 22 Ishwar Mill Lane. Well, his father was called, also SN Bose, was called Sreerup Nath Bose, and he was an accountant in the East Indian Railways, which is now the Eastern Railway. And an accountant was probably the highest an Indian could have risen in the service in those days. And he was a highly cultured man. So apart from his skills at accountancy, he also knew a lot of science. In fact, after retirement, he founded a small factory manufacturing chemicals. And we'll see that this love of chemistry, he communicated to his son, who held it for the rest of the world. And Bose's mother, Amodini Devi, Amodini kept the house, and she bore 7 children, which was sort of normal in those days. And Satyendra Nath was the only son, and then he had 6 sisters in succession. Well, here are the parents as they really looked. And if you look at the picture of Sreerup Nath Bose, you see that the son took after him. The pictures of the aged Bose, Satyendra Nath, can hardly be distinguished from his father. But that's, of course, only natural. Well, the young Bose, you see him here at the age of about 10. He was educated till the age of 12 in the local schools in that Gua Bagan area. And even then, he was known to be a bright student, especially strong in mathematics. In fact, what used to happen when he was small, his father would leave him a bunch of mathematical problems, not the ones on this thing, I've just shown you this symbolically, mathematical problems to solve before leaving for office. And when the father came back in the evening, they would all be neatly done. And the boy would be asking for more. So, this whetted his appetite for more and more complicated scientific problems. And perhaps it was very good training for him. At the age of 12, then, since he had shown so much promise, his father admitted him to the iconic Hindu school. Hindu school, it was the nursery of the Bengal Renaissance. Many of the famous people of that period were studied in Hindu school. And this is the beautiful neoclassical building in which the Hindu school was housed in those days. So just to tell you that times have changed, this is how it looks today. So we pay a price for modernity. Well, Satyendra Nath was always good at mathematics, but now he had a wonderful teacher. The Hindu school's legendary mathematics teacher, Upendranath Bakshi. I'm afraid I couldn't find a picture of Mr. Bakshi, so I've shown you a cartoon, but perhaps it looks something like this. So he was very fond of this bright student, and in fact, it's related that once Mr. Bakshi, he gave Satyendra Nath 110 out of 100 in his geometry exam, because Bose had not just solved all the problems in the examination, but he had solved each problem in more than one way. And how many of us are able to do that in an examination? It's difficult enough to solve most of the problems. And of course, the picture I'm showing you on the right is not the problems solved by Bose. It's just to remind you of the kind of complications you did learn in school on plane geometry. And the proud teacher used to say that one day this young fellow is going to become an Indian Laplace or an Indian Cauchy. Well, he didn't become a Laplace or a Cauchy, but he became great in his own way. Well, here I show you a picture of the College Square and College Street as it used to be in those days. On the right side, you see these pillars are the Hindu school, which I just showed you. And right opposite is Presidency College. This is Hare School. This is the Calcutta University Senate Hall, now again replaced by a modern monstrosity. But Hare School and Presidency College look the same. Of course, there are walls and many things in between now. But in 1909, Satyendra Nath Bose entered the famous Presidency College. And of course, this was also the home of the Bengal Renaissance, which is where Derozio and others had taught. And there he joined the Department of Mathematics. Expected, because he was so bright in mathematics. Now, at the Presidency College, he and his class were taught by a galaxy of really brilliant teachers. They were taught English by H.M. Percival and Manmohan Ghosh, and also P.C. Ghosh, who were the younger teacher. They were supposed to be brilliant teachers of English. He was taught mathematics by Charles Cullis and D.N. Malik, also famous teachers. Taught physiology by S.C. Mahalanobis, who was the uncle of Prashanta Chandra Mahalanobis, P.C. Mahalanobis, who is credited with the planning, 5-year planning in India. And the famous Acharya Prafulla Chandra Ray, chemistry. And last but not least, the renowned Acharya J.C. Bose, who taught him physics. So under the tutelage of all these brilliant teachers, Bose graduated with intermediate science in 1911 and with a BSc honors in mathematics in 1913. And he stood first in both the exams. Then he did his MSc in 1915 in a subject which was then called mixed mathematics and today which we would call applied mathematics. And this is actually his mark sheet. And once again, he stood first. And if you want to see the marks, here they are. It's astonishing, especially the 100. And I was curious to find out which paper he had got the 100 in. And it turned out that the 100 was not in any of the mathematical papers, but it was in physiology, which is even more surprising. Anyway, with all of this, he got him one more gold medal, and that's the gold medal of the University of Calcutta. He won that. And then, with all of this, while he was still studying for his MSc, he got married. And his bride was Ushabhuti Ghosh. She was the daughter of a prominent Kolkata doctor. And you can see even from this picture, you see his bride, who was only 11 years old at the time. But you can see that his father-in-law was a rich man. You can see the amount of jewelry he has given to his daughter, all gold. And but, you know, at those days, it was customary to take a dowry. But S.N. Bose refused to take the dowry. And he also, the other custom was, you know, if you had a wealthy father-in-law, he would sponsor your studies abroad. And that also he refused. He asked only one thing. He said, I have about 200 friends. Can you invite them all to the wedding feast and give them a good food? So this was quite amazing. First of all, that he had 200 friends and that he wanted them to be invited to the wedding, and that was done. And Ushabhuti, who was 11 years old at the time, later she bore her husband 9 children. Once again, this is funny today, but in those days it was quite normal. They lost 2 children in infancy. 2 sons and 5 daughters survived into adulthood. And they are the people who still live in that Bose house at 22 Ishwarnil Lane and have kept it in good condition. Well, Mrs. Bose was a very gracious and uncomplaining hostess, especially because her husband, as you have seen, had many, many friends. And these people would drop in all the time. And then Bose would say, So-and-so has come, he will stay to lunch. So-and-so has come, they will stay to dinner, and so on. And she was always able to provide something for that. In fact, I have read that Bose's friends used to describe her as Ma Annapurna because she always had food ready. Anyway, so here is a picture of Bose in later life. You see Bose in the center. He looks very much like his father. This is the lady now, much more than 11 years old. And here is the whole family with sons, grandchildren, daughters-in-law, sons-in-law, and so on. But anyway, getting back to the 1915, with his MSc passed with flying colors. Now what he found was that it's easier to get past the exam than to find a job. And so he found himself among the great ranks of the educated unemployed. So not surprisingly, since he was a married man, he was soon about to become a father, he had to earn a living, and he started doing that by doing private tuitions. Of course, with his renown as a good student, he could get a lot of tuitions. And one of his students at that point actually became a star. Unfortunately, not a star in science or mathematics, but a star of a different kind. That was Pramathes Chandra Barua, who, of course, was a very well-known film star in Bengal in those days, and is probably the first to have played Devdas. You see a poster of that Devdas with Devika Rani. And he also was the young heir of the Gauripur state, a princely state which is now in Assam. And as a result, SN Bose was paid a princely tuition fee, and that was 200 rupees per month. Now, I'll put this in perspective as we go. I'll mention further sums. So I assure it was a princely sum. And therefore, even if Barua did not excel too much in mathematics, there was compensation for this. Then came a lucky break. What happened was that Sir Ashutosh Mukherjee, who was a mathematician, who then studied law and became a famous lawyer and later a judge, he was appointed as the second Indian Vice-Chancellor of the Calcutta University in 1906. Before that, for a short time, Sir Gurudas Banerjee had been the Vice-Chancellor, but for only a short time. And Ashutosh Mukherjee became a reforming Vice-Chancellor and made many, many changes, mostly for the better, in the university. Among other things, the university did not have postgraduate departments. He started postgraduate departments in physics and chemistry. And the physics department started in 1915, the same year that Bose and his friends were graduating. Now, how did he do this? Sir Ashutosh, he persuaded two of his rich lawyer friends to donate generously for these new departments. Sir Rashbihari Ghosh donated 21 lakhs. Sir Taraknath Pali donated 14 lakhs. To put this in perspective, this happened in 1915. In the year 1913, Srinivas Ramanujam wrote his famous letter to Hardy saying, I am a poor clerk in the Port Commissioner's Trust of Madras, and my pay is 20 rupees a month. So it was possible for a clerk to maintain himself and his family on 20 rupees a month. So now you see that the 200 rupees paid to SN Bose was a very handsome tuition fee. And these amounts were simply astronomical amounts, also telling you how much lawyers made in those days. And if I convert them to modern figures, that's what it is. 250 crores from Ghosh and 170 crores from Palith. And I really wish my institute and perhaps yours had donors who were as generous, private donors who were as generous today. Well, with the help of this money and other things, Sir Ashutosh built up a truly stellar physics department, the like of which has not been seen in this country since. There was D.M. Bose, the nephew of J.C. Bose, who was the Ghosh professor, the first to be appointed in 1914, and C.V. Raman, of course, India's only science Nobel laureate till date, who became the Palith professor in 1917. These two chairs were sponsored by those gentlemen. There was P.C. Mahalanobis, who was also a professor, but he was in Presidency College. But students would go over to Presidency College to attend his lectures. In fact, we have done that also as students at one stage. And then there were these four young lecturers, all famous, Meghnad Saha, S.N. Bose, which we are talking about, S.K. Mitra, who brought radio physics and ionospheric physics to India, founded the radio physics department of Calcutta University, and B.B. Roy, who was a very well-known spectroscopist in his day, worked with people like Hertzberg and Bohr. Unfortunately, he is mostly forgotten. He's remembered only as a mnemonic, how to remember the color code on a transistor. If I remember it correctly, it is B.B. Roy of Great Britain, very good wife, which tells you which the letters stand for the letters of the colors in it. It'll be interesting to see how much they were paid. Well, very, very good salaries by even by modern counts. DM Bose was paid 600 rupees per month. Raman was paid 1,000 rupees per month. You can convert that into modern figures, and the lecturers were paid 125 rupees per month. And what did they teach? Mahalanobis taught mathematical methods. Atomic physics was taught by DM Bose. Quantum theory taught by Saha. Bose taught relativity. Waves and optics, as you would expect, were taught by Raman. Mitra taught radio physics, and Roy taught spectroscopy. Must have been wonderful to be in the department in those days. Things changed after 1919. In 1919, as you know, came the Jaliya Balabag massacre. And it marked, in a sense, the beginning of the end of the British Raj, because the indignation it roused across the country made Indians in their millions come out in their open to demand freedom. And you see this picture from Mahatma Gandhi's non-cooperation movement, which came in 1921. And people really came out in their millions, and the protests against the British Raj never stopped until we got our freedom in 1947. Now, of course, some such momentous events happening in the country had to have their repercussions in the university as well. Now, Bose, of course, was very sympathetic to the national cause, and he had friends who had actually had become extremists, but he did not participate himself in the non-cooperation movement. And in fact, Sir Ashutosh, who was the vice-chancellor, he did not approve of disorderly agitation either. Okay, he belonged to the old school. Anyway, he was a judge who had called out order in the court many times, so I think he did not approve of disorderly agitation. But 80% of the students of the university, they responded very enthusiastically to Gandhiji's call. They boycotted their classes. Students are always happy to boycott their classes, and publicly made bonfires of foreign goods. These were not those bonfires, but something like that. Now, of course, the government was not happy. The British government of those days was not at all happy. And they retaliated, as governments do to such protests, by saying that we are going to withdraw financial support to the university. No money. Unless 8 conditions, which were described by Sir Ashutosh as humiliating conditions, and essentially they would give the Sarkari officials complete control over the university's internal matters. Of course, Sir Ashutosh was not accepting this. He fought this tooth and nail. But by 1924, unfortunately, he was dead. And then what happened was that the government immediately replaced him by a person whom they knew would accept all their demands. That person did so, and therefore those conditions were there, and they are actually still there in the university rules and bylaws. So if all of this has a very contemporary ring, it just shows you that things don't change. Now, in 1921, when Sir Ashutosh was still fighting this, and it was likely that the financial support of the government would be withdrawn, then among the people who were supported by the government funds was Bose. So there was the danger that he would be out of a job as soon as the government withdrew the funds. And so at that time, he made his fateful decision to leave Calcutta University and to go to the University of Dhaka. Now, he would go there as a reader. It's a promotion above lecturer. And Sir Philip Hartog, who had been sent from London as the new and the founding VC of Dhaka University, you see here the beautiful Curzon Hall, built by the Dhaka Nawab to house the university, which was inaugurated by Lord Curzon, the Viceroy. And it was in this building that Sir Philip Hartog set up the university. The physics department is still there to the right. You see this gateway here behind the tree, and that if you go in, it's the physics department. So the new vice chancellor, he had handpicked Bose and some other bright sparks, including J.C. Ghosh and the historian R.C. Majumdar and others, and he persuaded them to move to Dhaka. The pay was also good. Remember, Bose was getting 125 rupees as lecturer. Now the pay scale was 400 rupees per month, with an increment of 50 rupees every year till it rose to 1,200 per month, which would be a very, very handsome sum. Well, with all these reasons, with his job there at stake and with this new and tempting offer, S.N. Bose decided to move to Dhaka. And so he did move to the river of the Padma, the land of the river Padma, and took the train to Gwalior Ghat, then the steamer all the way down the Padma to Narayanganj, took a train to Narayanganj, of course you can fly today, but and then reached Dhaka and participated in the setting up of the new university. Now, life as a pioneer is always hard. So a lot of things were not set up. In fact, so Bose, writing to his best friend Meghnad Saha in 1921, he writes, "It has been well over a month since I moved to your part of the country." This is where Saha came from. Work has not yet started. Your Dhaka college had quite a few things, but due to utter neglect, they are in a bad way. Perhaps I need not elaborate. On the table of the sahibs are scattered lots of Nicol prisms, lenses, and eyepieces. It would require a lot of research to determine which one belongs to which apparatus. We do suffer from lack of journals here, but the authorities of the new university have promised to place orders for some of them along with their back numbers. They are talking about having a separate science library. So you see that things were not set up at all, and he had to work hard to do that. And in fact, he did many things. He taught thermodynamics and electrodynamics. And at the same time, he was setting up laboratories and buying books for the library. So for my colleagues in IIT who complain about the teaching load and the load of administration, you see that it's possible to do absolutely top quality science even with so much of a load. Well, if you are S.N. Bose. 2 years later came a big jolt. Due to bureaucratic wrangling with the Bengal government, common feature of academic institutions, again the Bengal government also again threatened that we won't give you money. Dhaka University faced a financial crunch. And once the money was reduced, among other forced economies, Bose's regular appointment was changed to a one-year contract on a fixed salary with no promise of either an increment or of a continuation. So suddenly from a regular job, he had a one-year contract and with no guarantee. It could have gone after a year. So he must have regretted coming away from Calcutta University at that stage. Anyway, Bose fought very hard to keep his job. He wrote to the Vice Chancellor, "I shall be in Dhaka after the vacation and shall stay on pending the decision of the Executive Council, but I am afraid I can't give any undertaking to serve till 8th October, that was the end of the session. If the university authorities persist in their unjust decision, I shall have to seek for a job elsewhere." So he was threatening to leave, but of course that was not much of a threat because his job anyway would have terminated on 8th October. Well, the Vice Chancellor wrote back sharply, saying basically that why are you complaining? You're getting much more money than before, and just wait and see how things develop. But he was also a fair-minded man. So in March of 1924, he chaired a committee which resolved the following things. One is that Bose would continue to work till the end of the present session, that was till 8th October, on his present salary. Then he was to be granted 2 years study leave from the beginning of September 1924. So he could leave earlier if he wished. And he was to receive a total advance of 13,800 rupees, which given the fact that his monthly salary was 400 rupees, would be enough to cover his passage to Europe and his stay for 2 years there. So it was actually a generous grant. And this was given to him by his own university. And it was while all this tussle for money, for keeping his position, for setting up labs and so on was going, it was while this was going on that Bose wrote his famous paper on blackbody radiation. So now it's time for me to come to how he wrote that paper. So during the Durga Puja of 1923, Meghnad Saha came home to his village near Dhaka, I've already mentioned that, and naturally he came to visit his dear friend Satyendra Nath Bose. The two had much to discuss. And Bose, who was then teaching thermodynamics and blackbody radiation, among the discussions they had, he complained that the theory of Planck was hard to teach to students. They kept asking awkward questions. Of course, the theory is ad hoc, so they would be asking awkward questions. So Saha, who had recently moved to Allahabad University, which did get some better journals then, it was better set up, informed Bose about the papers of Pauli and of Einstein and Ehrenfest, which I told you about, the 1923 papers which followed the discovery of Compton scattering. Now, I should remind you that in 1903, Lorentz and then Fokker in 1914, they had shown that the momentum transfer between free electrons and radiation. So suppose you have a gas, think of the gas in this enclosure, and the blue things are free electrons and the red dots are photons. So of course, there is some energy transfer because of these collisions, but this cannot take place through radiation pressure alone. Remember, in 1903, people knew only about radiation pressure. And then Pauli showed that in 1923 that no, you don't need radiation pressure, but Compton scattering of the photons from the electrons can do the job. But for this, of course, as I have explained, he showed that he needed the Einstein equation, Einstein's derivation, and with this nonlinear term which violates causality. And Einstein and Ehrenfest had extended this calculation to atoms, but again based on a Maxwellian distribution. So these were the things which Saha was able to explain to Bose, and these were the developments. Well, Saha went back to Allahabad, but Bose kept thinking about this, and he decided to treat photons purely as particles, forming a gas just like molecules of hydrogen, oxygen, etc. do. Now, the statistical behavior of a gas had been worked out by Maxwell and by Boltzmann, and I will go through this part a little fast because most people learn it anyway, but I'll stress the important features of it. See, the phase space of a gas is a multidimensional space where you plot the coordinate on one side, on one axis, that's the x here, and the momentum on the other side. And of course, you have these little boxes with a small change in x and a small change in p, delta x and delta p. And each of those little volumes is called a phase cell. Now imagine the volume of the phase, the area of this particular phase cell is delta. Of course, this is only for x. If you take the y and the z also, then you will get a 6-dimensional space, and the volume will be delta cubed. It's delta for x and px. So for the other three, if you take all three, you get delta cubed. Now, Boltzmann had showed that if you take the number of phase cells lying between the energies E and E plus delta E, that's given by a formula like this. It's related to the E value of E, and you divide by delta cube because you take the phase volume and divide by the number of cells, and you get a number like this. Then you go ahead and calculate the statistical probability of distributing any particles among these cells. For this, what do? You simply count the number of configurations created by putting small e different particles in capital N different phase cells for this energy range. So what the idea is like this, that you have a set of boxes. Each box has a large number of compartments. So basically each box is analogous to a different value of E. And the compartments are the number N of different phase cells for every value of E. And now you're going to put a number of boxes. So you'll have to put a number of balls here. And the balls each have colors, so you can tell which ball is going where. And you're putting, let's say, 2 balls here. So that this N is 2, this N is 4, this N is 2 again, and so on. This N is 3. So how many ways can you make this distribution? Of course, this is a well-known problem in combinatorics. So the number is actually the capital N, which is the number of states inside a box, to the power of that number which balls you have put in the box, divided by factorial of the number of boxes. So when you take all the energy boxes into consideration, the total number of configuration, of course, this is the probability for one box to get one energy. To get all the energies, you multiply over all the energies. So it's a continued product, and then you multiply this to take care of the overall redistribution of the balls in the boxes. And N, of course, is the total number of particles. And N is the sum over all the particles. It could also be looked upon as the integral. Well, now you can find the entropy of the system by using the famous law of Boltzmann. So remember this W is the total number of configurations. So it's connected with the entropy by the Boltzmann law. S is K log W. And in this case, of course, I substitute for W this value which I have in the previous slide. The second law of thermodynamics, so that's the entropy for a particular distribution. The second law of thermodynamics now tells us that when the gas is in equilibrium, the entropy must be maximum. That is, the distribution of particles n, the small n must be such that the entropy becomes maximum. Subject to two conditions. One is that the total number of particles or balls is constant. The other is the total energy is a constant. So subject to these, you can now maximize it, and the distribution you will get for n is simply this, and this is the Maxwell-Boltzmann distribution. Okay, and this is your famous Boltzmann factor. Note something, there is no delta in this formula. The delta has cancelled. And now, therefore, you don't have to worry about that phase cell. You can take delta to 0 and have a continuum of energies and momentum of positions. So it's a sort of polite fiction introduced there, and which can be removed at a later stage. It's just a device. For an ideal gas where the particles don't interact, you get the famous Maxwell velocity distribution. You put this value of E in here, you will get this. And now this is the behavior. This is the Boltzmann distribution, and it's quite similar to the Maxwell velocity distribution. And of course, this is measured, it is well known. Now for photons, which Bose was trying to do the same exercise for photons, he made three very crucial physics assumptions. And this is very important because this is the most crucial part of this talk. First of all, he took this one-dimensional phase cell not to have some fictitious area delta, but to actually have the area H, Planck's constant. And what does that mean? It means that delta X into delta P is H. This is a result which we are all familiar with. This is the uncertainty principle. But the uncertainty principle of Heisenberg was to come 2 years afterwards, with a lot of very good logic. But Bose implicitly took it without knowing all the arguments of Heisenberg, but he did take it. He was the first person to use the uncertainty principle, perhaps without fully understanding why he was using it. This was one important physics assumption. The second physics assumption is that he assumed that the photons are not just identical, but they are indistinguishable. Now, how can two particles be indistinguishable? This can only happen if they are also in some sense waves, and with the wave-particle duality which came with Louis de Broglie, and that came after 2 years. In the next year. Bose did not know about it. And what it means is that if you look at the boxes here, the same boxes, but now the balls are not of different colors, but they all look the same. So if you take one ball out of the first box and put it, let us say, in the last box, and interchange the two, nothing will change. It's exactly the same configuration. So the counting has to be different. And that was taken into account. Now, this is an old problem of mathematics. There was no great mathematics done it. It had been solved as early as the 2nd century BC by Pingala, and then by many other mathematicians, Omar Khayyam, Lilavati, it's then the Lilavati, Rabbi Ben Ezra, Fibonacci, Cardan, Pascal, Leibniz, and last by De Moivre in 1711. It's called the problem of combination with repetition, and Bose must have immediately known the answer. And I can guarantee that because Bose, his textbook, the standard textbook was the algebra for the schools and colleges, with numerous examples by Todd Hunter. This was the standard textbook of those times, and he must have worked it out from the beginning to the end and maybe backwards during his school days. And this book, published 1889. And here on page 536 of this book, I don't know if you can read this, problem number 811 is to find the number of combination of small n things taken 1 to 3 at a time when there are p of one sort and so on. So this one reduces, if you take only things of only one sort, it reduces exactly to the problem which Bose had. And they are done by using letters and so on. So the number of configurations is actually given by this formula. Instead of the simpler formula there, it is capital N plus small n minus 1, factorial of that, by factorial of small n, by factorial capital N minus 1. And so all you now need to do is that take all the energy boxes as before, total number of the continued product of these overall energies. And then remember that these are photons in an enclosure. So unlike the Boltzmann gas, these photons are being absorbed and emitted all the time. So the total number is not fixed. So now we go with the same idea. Find the entropy. In this case, entropy is K log W, and this is the one calculation of Bose. And the second law says exactly the same thing. Distribution of small n will maximize this. Subject to, remember we had fixed total number and fixed total energy. Now we dispense with the fixed total number, only fixed total energy. And when you do that maximization, this leads to a distribution like this. Capital N over, you have the Planck formula. Already the Planck denominator has come. And only this arose from taking the photons to be indistinguishable, nothing more. So, but Bose's calculation of NE, this is the number, total number of boxes, for a particular energy, was also novel and far-sighted. He did not go with the calculation of Rayleigh and Jeans, which assumes waves, but he was only dealing with particles. So his assumption was the following. He first combined Planck's law and Einstein's mass-energy relation to write energy is momentum into velocity, which is true for light, and that's the same as Planck's law. And this immediately gives you the same as P is h over m. That's the de Broglie relation. The de Broglie relation 1 year before de Broglie. When you combine that, you take P as h nu over c, and the same number which you get, the number of phase cells will be, this is the total number, of course, in a shell, and you divide that by h cube, which is the volume of each cell. So that h cube was his new assumption. Okay, so if you go from momentum, use P momentum related to frequency by this formula, you can convert the number between nu and nu plus into this number. And taking this per unit volume, he immediately got the same number of photon states as Lord Rayleigh's counting per unit volume, which is this. This is amazing. It comes only from the assumption of the phase space. And when he plugged in his statistical distribution, this one, he arrived at this formula. So the average energy was now simply this. Okay, multiplied by n nu, which is, of course, so E nu is h nu. So you multiply that, you get this formula. So this has everything in the Planck distribution formula except the factor of 2. This is 4 pi h by 8 pi h. Otherwise, the whole formula has come. And this is where Bose's physical insight was at its best. The third assumption he made was that these must be angular momentum states of the photons, which remember were particles. So he assumed that they spin around their axes like planets. Remember, you've used the momentum and the energy, so there is only angular momentum left. So he assumed that they spin like planets, either clockwise or anti-clockwise, and therefore there are two different modes, and that's how he got a factor of 2. And this is the concept of an intrinsic spin 1 year before Uhlenbeck and Gauss-Schmidt proposed it. Once again, a fantastic discovery. Now, the unfortunate part of this story is that, of course, Bose did not realize how far-reaching his assumptions were. So he had uncertainty, he had the wave theory of matter, he had spin. But of course, he did not realize how far-reaching this was. But he did realize that his work was important. And therefore, he wrote it up in a modestly titled paper called Planck's Law and the Light Quantum Hypothesis, which doesn't tell you that this is a fantastic piece of work. Well, here is Bose's handwriting. This is not the manuscript of the paper, which has been lost, but this is a write-up which he later made for Einstein and was later found among Einstein's papers. So they have been preserved. Anyway, but full of confidence, towards the end of 1923, Bose sent his manuscript for publication to the very well-known British journal called the Philosophical Magazine. After 6 months, the journal sent back his manuscript. Those of us who publish regularly will have this experience with a curt note saying they couldn't publish it because the referee report is negative. In those days, the referee report was not sent. Only the editor's note came back, so he didn't even know what the editor had said. So in June 1924, with his paper rejected, with his job only till September, he took a bold step, or maybe a desperate step, and he sent his manuscript to Einstein. And he wrote this letter, famous letter, which is on the poster, but let me read it out to you. Respected sir, I have ventured to send you the accompanying article for your perusal and opinion. I'm anxious to know what you think of it. You will see that And he's very proud of his derivation of the Planck's law. So independent of classical electrodynamics. So he has defined only using phase space, no argument using waves and no argument using polarization. So anyway, then he goes on to say that I do not know sufficient German to translate the paper. If you think the paper is worth publication, I would be grateful if you publish in Zeitschrift Physics and so on. But then he says that I was the guy who asked your permission to publish, to translate your papers on relativity into English. And indeed, he had done that. He and Saha had published the first English translation of Einstein's papers on relativity, were actually by Saha and Bose, and he had made that translation in the year 1920. This is dated to 1920. So I'm not sure how seriously to take his statement that he didn't know enough German to make a translation. He had done it the other way, but maybe he was not confident that his German would be very high quality. But anyway, Einstein certainly realized that he understood German, so Einstein's answer was written in German. So here is Einstein's letter to him, which you can see is in German. And it's good that he addresses him. This is dated 2/2 July 1924, and he says, "My dear colleague." So here is the translation. But the great man, though he was supportive, he also defended his own work. But let me read out this thing to you. I've translated your work and communicated to Zeitschrift Physics. In fact, it came out under this form. It signifies an important step forward, and I liked it very much. And then, of course, he says, in fact, I find your objections against my work not correct. Like any good scientist, he was very defensive of his own work. But at the same time, he says, this does not matter. You are the first to derive the factor quantum. This is the Rayleigh Jeans factor. The quantum, theoretically, even though because of the polarization factor too, not wholly rigorously. Of course, Bose had not talked about polarization. I'll come back to this. Anyway, this is high praise coming from Einstein. It is a beautiful step forward. And then he has a friendly greeting from Einstein. And Einstein knew so little about India that even when he translated this paper, he didn't put Bose's initials. He didn't think they were important. It's by Bose. So let's go ahead with this. He added a note of support at the end, and because he was the editor, so he added this one. In my opinion, Bose's derivation signifies an important advance. The method used here gives the quantum theory of an ideal gas, as I will work out elsewhere. Not we will work out elsewhere. I will work out elsewhere. I'll come to that. Einstein neither invited Bose to collaborate on taking his work ahead, nor did he ask Bose to visit him at Berlin. In fact, he created a mess. When he made the translation, he didn't like Bose's idea of spinning photons, so he put back the polarization. Since Bose's derivation assumed particles only, polarization had no meaning. So having created the confusion himself, he then writes that it's not rigorous because of the confusion. So great men have their aberrations as well. And the result is that the idea of spin didn't get credited to Bose. It went to Uhlenbeck and Gauss-Schmidt. But the only person, in fact, who afterwards stood up for his spin idea was C.V. Raman. In a paper with Bhagavantam in 1931, Raman actually writes, we understand from a personal communication by Professor Bose that he envisaged the possibility of the quantum in possessing an intrinsic spin and so on. Anyway, that didn't happen, but Einstein's postcard did serve to smooth the path to getting visas for Bose's Europe trip. Though these visas for Indians were even more difficult to get than they are now. And this trip financed by Dhaka University, and in fact for the German visa, because at that time Einstein was still very highly regarded in Germany, the Nazi German. And so, therefore, in September 1924, Satyendra Nath Bose set out for Europe. In fact, of all his illustrious classmates like J.C. Ghosh and B.B. Roy and Meghnad Saha, they had all gone to Europe and come back before him. He was the last to go. And there's an interesting reason, which I can tell you perhaps later, but I won't interrupt the flow for that. Now, on November 18th, he reached Paris. But why Paris? Because in 1923, one R.L. Day from Dhaka University had been sent to work with Madame Curie at her laboratory, and Bose's mails were being sent today, so he needed to pick up his letters. And also there was some cheap accommodation to be had at the Indian Students Association. And some of Bose's old friend revolutionaries who had studied with him and then who had run away from British India and were lodging in France, they were also there. So he liked the place. He wanted to meet them. So he was advised that if he wanted to work in Madame Curie's laboratory, he should first meet with Paul Langevin. He was well known to be first Pierre Curie's student and also very close to Madame Curie. Now, Langevin had already read Bose's paper. He had been suitably impressed. And so he welcomed this young Indian with open arms. And from then onwards, for many years, he was a friend and mentor for Bose. Learning that Bose was interested in both crystallography and radioactivity, he gave him letters of introduction to both the great lady and to the crystallographer Maurice de Broglie, who was the elder brother of Louis de Broglie, who is famous for the wave theory of matter. Now, so Bose went to meet Madame Curie, and I'd like you to see this little clip which shows the real Madame Curie hard at work on some experiment, and she finishes that and she will look at you. So the Nobel laureate now, she greeted Bose warmly and said that since you are coming from Langevin, I will certainly allow you to work in the Radium Institute. But then she spoke perfect English. She said, you should wait till the new year and learn some French. Because your predecessor, Dr. Day, he did not know French, and so he had faced a lot of difficulties in working here. Well, Bose said that he was so awestruck on meeting this great lady, this heroine to the whole world, he forgot to tell her that he had learned French 10 years before. He could read, write, and speak French fluently. But he didn't dare to contradict the lady, so he just came away. And he reconciled himself to work for the time being in the X-ray laboratory of Maurice de Broglie. You see his picture here. And she did some crystallography there. Then, time went by. And as Bose remained in Paris, and then from the new year, 1925, he started working at the Radium Institute. And he loved the atmosphere. He learned cutting-edge experimental techniques from the experts. He had Langevin and Louis de Broglie to discuss theory. And he enjoyed the company of other Indian students and revolutionists in the house at Rue de Somera. And he also made friends among the Europeans. He made friends easily. So Bertrand Zadok-Khan, who was a young doctor, and his pretty sister, Jacqueline, who was then a school student, they were to remain his lifelong friends. And later they came with family and visited him in Kolkata and so on. Meanwhile, Einstein had translated and published a second paper by Bose, sent shortly after the first one. In this one, Bose had considered an ideal gas, massive particles with statistical equilibrium with radiation, which was the same problem which Einstein and Pauli and others had been doing. And he found that you don't need to take any interaction. You just take the same statistics, assume that the massive particles are distinguishable, the photons are indistinguishable, you will get the right distribution. The massive particles will have a Maxwellian distribution, photons will have a Planckian distribution. And so no interactions were needed at all for this, only statistics. And Einstein had translated this, and you can see Einstein's confusion with India still, because now he has the initials this time, S.N. Bose, but instead of Dhaka University, he writes Romna. And Romna is actually the location, is the exact address where the Dhaka University is there in Dhaka, but it's not what you would write, right? I mean, you would prefer to, say Dhaka rather than anyway. Well, Bose wrote to Einstein immediately on arriving in Europe. He writes to him as, "Dear Master, I have been granted leave by my university for 2 years," and he asks whether he can come and work with him. And Einstein is polite, and he says, "Thank you sincerely. I'm glad that I shall have the opportunity soon of making a personal acquaintance." And then he says, "Your papers have already appeared. The reprints have been sent to me instead of you, but you can have them." Then he says, "I am not in agreement with your basic principle," because he's still defending his thing that interactions are needed to get this thing, and statistics alone is not enough. Well, while he was sort of not agreeing with Bose on this, he was feverishly on his own developing Bose's idea. In July 1924, as soon as he had got Bose's paper, he had worked on the statistical distribution of the atoms in a monatomic ideal gas, which today we would call a massive boson gas. That's this paper. And then came this paper in January 1925, when Bose was in Paris. He showed that the molecules in a massive boson gas tend to cluster at the ground state, the phenomenon which we today know as Bose-Einstein condensation. This is purely a discovery of Einstein, but of course completely using Bose's statistics. And the point is that he also found in Bose's statistics the missing piece in his own theory of specific heat. So I'll just skim over this a little bit. Einstein had been assumed it, and then what he needed was a Planckian distribution of oscillators in the solid. Now he only had to call the oscillators bosons. And of course, today we call them phonons, and they are quanta of sound. In all these papers, Einstein scrupulously acknowledged that the statistical method had been discovered by Bose, but he was not going to share the glory of these further discoveries with an obscure Asiatic, whom he had never met. So that he was very clear about. In fact, it was Paul Dirac who made Bose virtually immortal when in 1926 he coined the expressions Bose-Einstein statistics and Fermi-Dirac statistics. Note something, Bose-Einstein is alphabetical, but Fermi-Dirac is not. In excess of modesty, he put his name after Fermi and named the particles fermions. And of course, to match the other type had to be bosons. These names have stayed ever since. But the fact that Einstein had displayed great selfishness in the work, it never bothered Bose. To him, Einstein was the master, and it was always the master. So after a whole year in Paris, he was finally able to move to Berlin in October 1925 and meet his hero. And Einstein was then the director of the Kaiser Wilhelm Institute of Physics, today called the Max Planck Institute. So a little clip from there, Einstein at the Kaiser Wilhelm Institute, but there were many other luminaries in the Kaiser Wilhelm Institute. There were a fair number of Nobel laureates: Planck, Nernst, Hahn, Meitner, von Karman, Schiller, Wigner, Debye, Hermann Mach, the crystallographer, and Fritz Haber's process. But everything revolved around one man with a mustache, and he was the sun around which all these planets revolved. Well, in 1925 came the new quantum mechanics. This is important, the famous papers of Heisenberg, then born in Jordan, and then Heisenberg born in Jordan. And this created a furor in the physics world of those times, and the best, in Bose's own words, writing to Jacqueline Zadokan, who was still in high school, he writes, everybody seems to be quite excited in Berlin the way things have been on with physics. First, on the 20th October, Heisenberg spoke about his theory. Everybody is quite bewildered, and there's going to be very soon a discussion of Schrödinger's papers. Einstein seemed quite excited about it. The other day, coming from the Colloquium, we found him jumping in the same compartment where we were, and forthwith he began to talk excitedly about the things we have just heard. We were all silent, but he talked almost all the time, unconscious of the interest and wonder that he is exciting the mind of passengers. So you see the kind of excitement which was raised by the new quantum theory. And in fact, Einstein suggested to Bose that we should use this new theory. And one was his old bugbear, whether their new statistics implied some subtle interactions between the photon himself. He could not get out of this. And the answer is that it does not. And the second one was to ask a question, how could the transition probabilities of the spontaneous and simulated emission, that's his A and B coefficients, be derived in the new quantum mechanics? Now, this is a problem which was far beyond the capacities of people at that time, because it is now done by a perturbative calculation in the dipole approximation. We know how to do it today, but certainly it could not have been done in the early stage of quantum mechanics in those days. The perturbation theory itself had not been developed. But anyway, not surprisingly, Bose did not make any headway in either of these problems. Instead, he started working in Hermann Mach's crystallography lab, because he had already been doing some work with Maurice de Broglie, and he started doing that in Hermann Mach's crystallography. He did visit Einstein regularly and had all manner of discussions with him on everything under the sun, including physics, but these two problems remained unfinished. So he never wrote a paper with Einstein, and in mid-1926, he came back to India. Working with Einstein, of course, was not so easy. And a close friend of Bose had described how many years later he opened up a little bit about his experiences with the great man, and they were not all that pleasant. He writes, one day Bose was reminiscing about his Berlin days. Einstein had given him a problem to solve. Satyen Babu told me, I thought about it for 3 days, and then I went to see him with my solution. Einstein went through it and said, well, this is not wrong, but not the way I want it. This clue does not open up any new possibility. Please don't waste my time with such trifles. That is what the old man said. Satyen Babu's mind seemed to go back to the past, and for some time he did not speak. And of course, it was incredibly rude of Einstein. But the truth is that he was now 46 years old, and he didn't like being proved wrong any more than anyone else. And this interaction business kept rankling with him. And in fact, Einstein's great creative period was more or less over. I mean, the work which he had done following Bose was almost the last, and there's only one piece of work after that which really is remembered. The rest was all on some blind track. Anyway, he succeeded in putting Bose off from theoretical physics. So Bose did not publish again in theoretical physics till 1939, 16 years later. So that was actually the real effect of working with Einstein. Well, I'll now come to the last part. I'm already over time. So I'll talk about the rest of Bose's life. Sort of I'll telescope it into a few slides. So as the sage of Kolkata, well, at Dhaka. So Bose returned to Dhaka to a hero's welcome. He didn't have a PhD, but he had reference letters from Einstein, from Lajoie, from Hermann Mach. And so in 1926, he was appointed. So from almost losing his job in 1923, he was now appointed professor and head of the Department of Physics at Dhaka University. So that's nothing succeeds like success. And after 1 year, he was also made the Dean of Science. So now as Dean of Science, he set up laboratories in chemistry, optics, and crystallography, and he started publishing in these areas, not in quantum statistics. In 1938, 10 years later, he was offered the Palitz Chair in Physics at Calcutta University. C.V. Raman had moved to IISc as its director, but Meghnad Saha liked Dhaka. He enjoyed Dhaka. He was not coming away from Dhaka. The position of Palitz Chair was taken by Meghnad Saha. And then he stayed there. So I'm happy to show you this picture, which I was able to take last year with another very famous physicist. You can recognize Ashok Sen in the middle. This is the room of the head of the department, or the chairman of the physics department at Dhaka University. It's still there, more or less as it was in Bose's time. And you see the board at the back as the name of the previous chairs. And you see S.N. Bose from 1926 to 1945, a period of 19 years, which is sort of unprecedented. All the others have done shorter terms, 3 years, 5 years, and so on. Well, what was he doing there? Here are some of the papers he wrote. Electrochemistry, nuclear physics, statistics. And this D2 statistic, of course, is the Mahalanobis measure done by his former teacher, Mahalanobis, former colleague. Well, radio physics. Then he comes back to studies in the Lorentz group. Now he's back to theoretical physics. And in 1940, he now starts working on quantum mechanics. And here is a paper on the inhomogeneous Klein-Gordon equation. Then back to chemistry. Again, now fully in quantum mechanics, Dirac equations and the Zeeman effect, integral equation for hydrogen atom. In 1945, he left Dhaka. It turned out forever. He accepted the Khaira professorship at Calcutta. And he had explained that in the Hindu-Muslim riots, which were sort of happening every day there, and a feeling of insecurity in East Bengal, which was soon to become East Pakistan, must have prompted this decision. For, as you see, he had come to love Dhaka. He had refused the professorship earlier, but now he felt incumbent to leave and to come back. And, well, Dhaka has not forgotten him. And here is a picture again, which I took in Dhaka University. They have preserved S.N. Bose's room. This is the table and the chair on which he used to sit. This is the revolving chair at the back, and the table at which he used to work, and his bookshelf. And they've kept his office exactly as it used to be, as a sort of museum. In 1947 came independence, and then the second partition of Bengal and the horrors associated with that, the displacement of population. If these pictures look surprisingly contemporary, don't blame me. But, you know, when others who were his contemporaries, they became nation builders with the new nation, Bose was content to remain a scientist. You know, all the others, and from left to right, Mahalanobis, Bhabha, J.C. Ghosh, Bose, Saha, Sarabhai, and Raman, they all built up institutions, which are still some of our major institutions, and I work in one of them. IIT Guwahati is another one, because the IITs were set up by J.C. Ghosh. But Bose never set up any institution. He didn't get into that. He was indeed nominated as a member of the Rajya Sabha, and he did accept it. And he remained a member till 1959. But he spoke only rarely, and just 3 speeches survive. One where he opposed exceeding the power by the judges, one on solving the refugee problem, and one on the role of the newly formed UGC. And again, if these have a surprisingly contemporary ring, don't blame me. It just shows how little the country has changed. Well, Bose retired from Calcutta University at the age of 62 in 1956. But before his retirement, suddenly he started working at a tremendously accelerated pace on the unitary field theory, which we today call the unified field theory of Einstein. So one paper in September 1952, January 1953, July 1953, again July 1953, and January 1954. 5 papers within a year and a half, which was unusual because normally he wrote a paper only maybe once in 2 years, and it was be a long and thorough, detailed paper. So he suddenly worked on this. And at this point, Einstein, who was at that point totally isolated because nobody else was working on his unified field theory, suddenly he realized that here he had somebody, a kindred spirit. And at that point, Einstein was very old at that time. He now wrote to Bose. This time he really wrote to Bose, inviting him to come and work with him in Princeton Institute of Advanced Studies. And Bose was all ready to go. He was retired anyway. He had freedom to go if he wanted to. However, Bose was refused a visa, US visa. It was the height of the McCarthy period in those days, with a lot of paranoia about communism. And Bose had committed the mistake of visiting Russia and giving talks there. So that was on his passport, and his visa was refused. Then Einstein had to personally intervene and say, no, this person is not a communist and he's a great scientist and you should invite him and so on. So eventually Bose got the visa. Alas, when he had got the visa, Einstein had passed away. And you see Einstein's chair and desk as he left it. And so Bose was actually never able to really go and write a paper with Einstein. Surprisingly, that in 1994, when a stamp was brought out on SN Bose, what we find in the stamp is this formula, which has to do with the unified field theory, Einstein unified field theory, actually the torsion. And this is not Bose's great work. This is this last work. And I'm surprised, I don't know why it was put here, but it seems that somebody thought it was of importance enough to put here. Well, Bose had his little stint in administration. He was appointed the Vice Chancellor of Vishwabharati, the university set up by Rabindranath Tagore, as we all know, at Shantiniketan. But after 2 years, he resigned, and he said he was fed up because people would not let him do anything there. For everything, people said, this is not how Gurudev thought about it. And again, if this has a contemporary ring, don't blame me. Well, Bose was elected a Fellow of the Royal Society as late as 1958. And this is a story, he had been forgotten. And Dirac visited Kolkata and he had some discussion with Bose and then said, when you come to the Royal Society meeting, we'll continue this discussion. And Bose told him, I'm not a member of the Royal Society. I'm not coming to the meeting. So Dirac went back and he happened to be the president of the Royal Society. So he went back and immediately nominated him, and that's how Bose became an FRS. It tells you something about the nature of the world. More honorably, he was appointed the National Professor for 5 years in 1959. And then every 5 years that was renewed till his death. Calcutta University made him an emeritus professor and gave him a lab and grants to work through the Indian Association for Cultivation of Sciences. But he was now 65, certainly not a creative age, but he continued to train students in experimental techniques because experiment is where his real love lay. The other love he had was for getting the science in the mother tongue. Again, very contemporary issue. The Bangya Vigyan Parishad had been formed with Bose as its president, and his experience in Europe and Japan may have influenced him. In 1967, he was appointed president of the Indian Statistical Institute at the age of 73. He would remain president till his death. A few pictures. This is Bose with Paul Dirac, who is a head taller, but still a great admirer of Bose. This is Bose leading the convocation procession at the ISI. with academician Kolmogorov. He's the president, he's leading it. There's Mahalanobis at the back, who's the director of the ISI, and Kolmogorov as the chief guest. This is Bose with a young Indian astrophysicist, cosmologist, who we know today probably doesn't look like this anymore. This is Jayant V. Narlikar. Well, 1974 was Bose's 80th year, as well as the 50th year of the discovery of Bose statistics. So to celebrate this, year-long celebrations were held in Kolkata and elsewhere. It was a long round of seminars, symposia, felicitations, cultural programs. And not surprisingly, with the man of Bose's convivial character, he participated in these with himself, with his customary enthusiasm. And in fact, he was happy that he was getting the recognition, which he was long withheld from him. And he felt vindicated. He said, now I feel I do not need to live any longer. He felt that his life's work was done. So I'll show you this little clip, finally, of Bose himself from one of these felicitation meetings. It's a very short clip, but you see Bose speaking at the meeting. Unfortunately, the excessive strain told on his health. He was 80 years old, and 1 month after his 80th birthday, in February of 1974, he passed away quietly at his Kolkata home. And in Kolkata, not since the death of Rabindranath Tagore had there been seen such an outpouring of public grief. The procession which followed his funeral was more than a mile long. And people realized that they had lost a great luminary in Bose. So, of course, the flames consumed Bose's, whatever was left for Bose. But the flame he had lit for quantum statistics, that lives on, and that will continue to live on so long as we work on quantum theory and work with elementary particles. Now, finally, and I know I'm far over my time, but I apologize, but I wanted to say a few words about understanding Bose, because he's a man about whom many positive and also many negative things have been said. The first thing to understand is that he was a complete product of the Bengal Renaissance. He was a mathematician, a physicist, a chemist, spectroscopist, musician, a great conversationalist, a bit of an administrator, not too good at that, man of letters, a gourmet, he loved food. Well, as a Bengali, he would expect that, right? A family man par excellence. And he was full of the milk of human kindliness. He helped many, many, many people, in a quiet way. The 1923-24 work, as we have seen, it bridges the gap between old quantum theory and quantum mechanics. In a way, as I have shown you, he used the results of quantum mechanics. So, he could see quantum mechanics, as to quote Shakespeare, as through a glass, darkly. I mean, he had some fuzzy idea, not very clear ideas, but he was before his time. When quantum mechanics actually came, clearly he didn't like it. He didn't work on it till it had become much better established and so on. It took him many years to do that. For whatever reason, he didn't like the quantum mechanics. He started working on other things. But what I would like to stress is that his great work was not achieved by serendipity or by stumbling on some result, but by deep reflection and some absolutely amazing physical intuition. I say this because 5 years after Bose's death, there came out a very uncharitable article by a very famous person, Max Delbrück, who was a physicist who later became a biologist and won the Nobel Prize for Medicine. In 1979, he brought out this article, Was Bose-Einstein Statistics Arrived at by Serendipity? And this, in my view, is a horrible article in which he says that he points out that my contention that it arose from an elementary mistake in statistics that Bose made. If you go through the paper and you read Bose's paper, you will see that Bose has nowhere made the assumption which Delbrück thinks he made. So Delbrück is not able to understand how Bose could arrive at that. So he invents a mistake which he thought Bose may have made, and then says Bose made that mistake, and therefore he stumbled at the result. It's simply a ghastly and horrible paper and completely unworthy of a scientist of the standing of Max Delbrück. So my resounding answer to this is Bose-Einstein was not arrived at by serendipity, but by some amazing physical intuition. One of Bose's students in the final years, he wrote a very sensitive and understanding view of Bose, which I will read out to you. One should not expect people like him to be doing routine work in one particular line. That would be insulting him. They are after the final, they means people like Bose are after the final truth, not caring for what can be achieved on the way. So not caring about his publication list, as most of us do. Everything is eternal. He was not interested in small matters. He wanted to go for the depths. He was an aristocrat. An aristocrat of science is a good way to describe Bose, because he was undeniably the founder of quantum statistics and therefore a pioneer of a great deal of modern science. And I think there is no reason to ask, what else did he do? Why didn't he do things in a different way? After all, this is enough to put him among the ranks of the immortals. Does one ask, what did Dalton do after formulating his atomic theory? No. What did Neil Armstrong do after visiting the moon? What did Tulsidas write after writing the Ramcharitmanas? No. What they had done was enough to make them famous and immortal. And that is true for Bose too. And therefore, let me end by showing you this picture of Bose trying to get his dinner at Vishwabharati, and what is clearly an international conference. I show you his famous formula at the top, this time the right formula, and say a big thank you to Bose and a big thank you to all my listeners who have listened to this very long talk with a lot of patience, and I hope you enjoyed some of it. Thank you.
Thank you, sir.
Yes.
Thanks a lot.
Yes.
So marvelous chat.
You're welcome. Thank you. I'm glad you enjoyed it. Thank you.
So this is the beauty of the having Sreerup to giving the popular lecture, and the charm he spreads among the audience across the generation. So really we got mesmerized by all the details, and many of us got an opportunity to learn many things from your talk, Sreerup. So thanks a lot, and we are quite fortunate to be witness of this historic talk. And now floors are open for question and answers. So already time is quite long. So we will be able to take few questions. So please.
Yes. So maybe just a few urgent questions. Yes.
Yeah, can I say something? Sreerup.
Yes, please go ahead. Yes.
Yeah, I just want to suggest you is that why don't you convert this talk, or if you have already done, then it's this thing, not in my knowledge. Why don't you convert it in a form of an article and try to publish it, because this is what also we need to do for our own.
I know. Actually, there are very many good articles on SN Bose, but maybe at some stage I will do this. I will write an article, but some of them are also written with a slightly old-fashioned perspective, and maybe I would do that at some stage.
Yeah.
So at the moment, I'm glad to present it, but yes, I would write it at some stage. Yes.
Okay. Very good talk.
Thank you. Any urgent questions, especially from the students? Something you would like to ask or understand?
I think
hello, sir.
We are all
Yes.
overall.
Thank you.
Yeah.
Thank you.
So this question is a little bit off track actually.
Yes.
So I am like I want to know about the thing. So when we are lowering the temperature, so we are like getting into the quantum statistics. It's like bosons and fermions both are there. So
Yes.
yeah. So when we are lowering the temperature, the bosons we can get like I can understand. But while we are like talking about the fermions, so there is probably exclusion principle.
Yes.
Yeah. So so in that way, when we start saying in the reverse way, like when we are giving temperature to the system, so where that Pauli principle go from that system, so it can
Yes.
behave like classically.
Yes. Well, I think I'll try to answer your question in a more coherent fashion. So the Bose statistics comes if you look at that counting method which was put here. So you look at the particles as identical, right? All white pills. You think of the white boxes which I had there, and you have all these white balls, and you can interchange any of them. But now you can put any number into any box. Okay, the number which you put into a box is not restricted. Okay,
Yes.
so that gives you a particular counting, which is Bose's counting. Okay,
Yes, sir.
now the Pauli exclusion principle will tell you that you can put only one ball into one of these little compartments. You can't put more than one. In the
Yes,
Bose,
sir.
you can put any number. So if you
Yes,
do
sir.
that, the counting will clearly be different. Okay.
Yes, sir.
And if you do that counting, you will get a different total number of combinations. You put that into the probability formula, you will get the Fermi statistics. Okay.
Okay.
That's how it comes. Now, both the Bose and, let me finish. Let the Bose and Fermi statistics, they have this factor e to the minus e by kt plus or minus 1 at the bottom.
Yes, sir.
Now, if you go to low temperatures, if temperature becomes very small, then the e by kt becomes very large. So exponential of that becomes very large, and the 1 can be neglected. So in either case, whether it is plus 1 or minus 1, you just get the exponential factor, which is the Boltzmann factor. So at high temperatures, you get, at high temperatures, you will, it will reduce. Either way, you will get the Boltzmann statistics. Whether when you have when the plus or minus at the low high temperature means high energies. Okay, at low energies, of course, then this quantum nature will show up. But it's always there. It's not that it's gone away. It's simply because you can neglect it that the same behavior will show. Okay.
Okay.
So
that part I understand. But my question is something different. So the asymmetry of wave function. So
Yes.
in Bose statics is symmetric, and for muonic case is asymmetric. So antisymmetric.
yes.
So while we are heating system, both goes to the Boltzmann statistics. So
Well, let me yes. The Boltzmann, the wave functions remain symmetric or antisymmetric, but they just go up to a higher energy state. And at that energy state, the measurables which would be able to tell you the difference between Bose and Fermi, those measurables become negligible. So that's why it looks like Boltzmann statistics. There is no such thing as Boltzmann statistics. All particles are either bosons or fermions.
Okay, sir.
Okay.
Yes.
Boltzmann
Yes,
is just a classical limit. It's a fiction.
okay, sir. Thank you, sir.
Okay.
So any other question? So Raghunandan, you have a question, you can go ahead.
Yes. Oh, he has asked. I read what he has asked. He asked that simulation I showed in the beginning. So there were three colors there. There was a green, a red, and a blue in the middle. So the green is the normal phase. The red is the Bose-Einstein phase, and in the middle there is a sort of mixed phase. Okay, it's like you have a type 2 superconductor, you get a mixed phase. So that's what a typical ball of this BSC looks like. You see, BSC you have to confine into a ball using magnetic fields and so on. So the three phases separate out like that. That's what the three colors represent. Of course, you don't really see those colors, right? I mean, that's just a computer simulation.
Any other question?
Sreerup, I have a
Yes.
question.
Yes,
Simon
please.
here.
Yes.
Yeah,
yes.
so this is not related to the physics part. So you showed that this the contribution in building Calcutta University, the contribution from Sir Rajbihari Ghosh and Sir Taroknath Pali.
Yes.
And if I remember correctly, the contribution from Sir Rajbihari Ghosh was much more, compared to Taroknath Pali. But the salary of
Yes.
the professors
Yes.
who were having the named chairs, the salary was just the opposite.
Yes.
I think Pali
Yes.
professors were getting more
Yes.
salary than the.
Yes.
So was there any reason
So
for that?
Well, I think the point is that when the first professor to be appointed was, so the administration of the money was left to Sir Ashutosh. And I think when DM Bose was offered the job, he was happy to come for 600 rupees. Okay. Because that was far more than he could have got in any other position. He was a lecturer in City College at that time. Okay. In North City College, where he would have probably got about maybe 120 rupees. Okay. So he was happy to come for 600 rupees. Now with Raman, it was different because Raman already had a job. Raman was working in the audit and accounts service as an accountant there, and his salary was 2,000 rupees a month already there.
Okay.
So Sir Ashutosh, he actually came for half the salary, but he couldn't be offered 600 rupees. So Sir Ashutosh offered him 1,000 rupees, saying, "This is the maximum I can offer you." Well, Raman came for half the salary because he wanted to do science. I wonder how many people will do that. This is especially true for IIT students who should hear this and think about it. So,
thank you, Stu.
Yes,
it was a wonderful talk.
Yes, thank you. Somebody asked a question about Bose's participation in the freedom movement, if I remember, and I should yes. So let me just answer that first of all. Actually, one of the classmates, 1 year junior, one of the batchmates, close friends of Bose and of Meghnad Saha, was Barin Ghosh, who was the younger brother of Sir Aurobindo, and as you know, one of the major people in this Alipur bomb conspiracy, who spent many years in the cellular jail at Andaman and so on, and he was a close friend. And for that reason, SN Bose and Meghnad Saha, when they were students, even when they were students, they participated in the freedom movement by trying to do adult education and to teach young people, to believe in their own nation and future. So he was very much of a nationalist. It was there. He did not actually participate in protest because he was getting his salary from the British government. So he felt that he couldn't afford to lose his job. But the sympathy was there. And another of their very close friends, called Sailen Mitra, was actually he was participated in this extremist agitation, and then he had to leave India and finally ran away to France and to Canada and so on. So it's interesting that we know much later now, because the archives of the state have been opened, and we see that the police, the British police, had both Saha and Bose on their radar. And in some sense, they were regarded as terrorist sympathizers, according to the British. I mean, of course, they never participated in that kind of activity, but they were certainly not great friends of the British. And this is one of the reasons why the British textbooks and so on have consistently downplayed the work of both of these people. It's possible that even the fact that they were denied Nobel Prizes for what certainly was Nobel quality work could have come from the fact that the British government didn't want to push them. You must remember that in the 1920s, even Rabindranath Tagore was regarded as a terrorist sympathizer, because after Jallianwala Bagh, he returned his knighthood, and there were British spies in Shantiniketan spying on him all the time and reporting back, say, whether he was actually, the school was actually, whether he was training terrorists or not. So it was a different country. These people were very much supporters of the freedom struggle, but they wanted to participate not by getting into politics, but by building up the country's science in some sense, which is the same idea as other people had, and building it up in such a way that we could sort of, we could walk with our heads high in this scientific world. Yeah.
Thank you so much, sir, for the answer. So I have a small follow-up question.
Yes.
Do you think this could be one of the reasons why Indian science couldn't flourish too much at those times? Because if you were not sympathizing with the British, you couldn't really get too far.
Well, Indian science certainly faced a lot of problems in the colonial era, because it was, Indians were encouraged to do good mediocre science. But when they really started competing with the best Europeans, then they faced a lot of problems. This had been worse in the previous generation. It was not so bad in this generation, because after all, you see that Bose's trip to Europe had been financed by Dhaka University, which was then had a British vice chancellor and was sort of a government setup. So it was not all that bad. But yes, certainly they could have done, the colonials could have done more. But of course, these people were able to do very good science all the same. So I'm not sure whether your answer is a simple yes or no to your question.
Okay, thank you, sir.
You're welcome.
So there is one question by Chandradeep. Chandradeep, if you are there, you can ask your question. So Chandradeep has written here, sir, you have mentioned that S.N. Bose did not like quantum mechanics. Can you please tell something about his vision about modern quantum mechanics?
Well, there are various talks he gave later. So you see, Bose, as you have seen, he was there, very much there when the quantum mechanics came. And he, in some sense, as I told you, he was always enamored of Einstein. And this Einstein, he became as you know, Einstein famously didn't like quantum mechanics. He didn't like the idea of probability. And what is surprising is that Bose followed him in that. So Bose, who was an apostle of using probability ideas for his own famous work, but he didn't think probability was a fundamental thing in nature. And therefore, when probability and statistical ideas came into quantum mechanics, somehow he went with Einstein to think that this is not the final theory and you should do something else. So he just didn't get into it. The very fact that, there's a wonderful new ideas coming up, and all the people, who worked on quantum mechanics, even on the smallest things in the early days, all of them have their names in the textbooks today. Why didn't S.N. Bose do it? Clearly, he didn't like it. And later he has actually mentioned that in some of his talks, that I didn't think quantum mechanics was going to last long. I thought it was just some temporary thing, some kind of effective ideas, and a better theory would come up very soon. So he has actually said that. Of course, that didn't happen. Quantum mechanics turned out to be the best way of expressing reality. But, everyone doesn't always know what's happening in the future.
So I'm quite sure that we will keep on going on for question and answers. And
Hi, sir.
Can I ask one question if there's time remaining?
Well, last two questions then.
Last two questions.
And then we'll stop. Yes. Please.
Okay.
Yes, madam, you asked first. All right. Yeah. Okay, whichever.
Okay, sir. Actually, sir, first of all, thank you very much for this wonderful talk. Actually, I was wanted to add a little information. Actually, Dr. Purnima Sinha, who is just PhD from PhD from Calcutta University, she has also done her work under the supervision of Dr. S.N. Bose on crystallography.
That's
so
right.
I think that this part is left in this talk. Like, we haven't seen S.N. Bose as a teacher. He has.
Well, if I have to tell you everything about S.N. Bose, then I would have to give you a talk for 6 hours at minimum. So there are some things I had to leave out. Yes, there were many famous students of S.N. Bose, including Dr. Khastagir, who's replaced him, who was a very well-known crystallographer, who replaced him as head of department in Dhaka and also later came back to Calcutta University. There were many people indebted to Bose in many ways. But you are right, the first Indian physics PhD was by Purnima Sinha, and S.N. Bose was S.N. Bose's last student was Professor Partha Ghosh. Some of you may have seen him on TV and so on. He was a very prominent figure. He's still a fairly prominent figure on science. So, thank you. Anyway, thank you for mentioning that.
Thank you.
Yes. There was one other question, I think, please.
Professor Sreerup, thank you for such an engaging talk. I just wanted to ask this question. Like Einstein, in his research on unified field theory, he assumed that this torsion tensor is non-zero in order to recombine electrodynamics with general relativity. But in the postcard that you showed, it was commemorating Bose's research. It showed that the Einstein torsion tensor is non-zero. So was it an original contribution of Bose, or was it, an idea of...
No, that was the original, that was Einstein. So I don't know how that found its way into that post. I just present it to you as a curiosity. The idea that the affine connection is non-symmetric, that was all Einstein. And that gives you a torsion, and of course then he related the torsion field to the electromagnetic field tensor. And S.N. Bose followed that. He was basically trying to find solutions to the Einstein equation, unified field equations, and which he did. And actually, this is something I learned from my very revered teacher, Professor Amal Raychaudhuri. So he actually gave a talk on these papers by Bose at one stage. And of course, I was sort of too immature at that time to understand them well. But I remember the one thing that he said, that each of these papers gives a solution to the unified field, but they are not physically interpretable because that is not the right theory. But so Bose was really good at finding mathematical solutions. That's where his real skill lay. So, but that is not Bose's original contribution. And as I said, I was surprised to see that on the stamp rather than the Bose statistics.
Okay, so everything has to end at some point, okay? But Sreerup, one technical question is coming. Would you like to take? Very technical question. Yeah,
Okay.
question is by quasar supernova. So can you please ask this question? If you are there, can you ask this question?
Yeah, this is completely unrelated to the brilliant talk that Professor, but I'm really thankful that he is here and with all of us and gave this wonderful talk. But this is a very recent development on some experiments on positronium, and they are finding some anomalies, meaning that it's disagreeing with QED calculations. I was just wondering if he has any thoughts about why that might be. This is unrelated to today's talk.
Well, I'll give you a short answer to that because it's really a highly technical issue. But first of all, the discrepancy is not at a level which would make it, completely well established. It seems to be a hint of a discrepancy, but it's still not at the statistical level where you would say it's a big discrepancy. The second thing is that this is a highly accurate measurement, so it requires QED at a very high order. And these high order calculations of QED, always, the theoretical calculation is a bit suspect because it involves a lot of computation. Okay, most of there are just too many diagrams in QED at that level to be able to do by hand. So it's all done on the computer. And then if you made one little programming mistake, you had it. I don't know if you remember this, but about 10, 12 years ago, there was a similar big discrepancy in the calculation of the anomalous magnetic moment, the G-2 of the muon. And then it turned out that there was just one sign error which had caused the whole thing. And that was due to a misunderstanding of a computer program. So I would wait a little more. This is certainly an intriguing result, but I would wait a little more before I would say that this is telling you something really exciting. So in my experience, I have seen many such results come and go. So I'm would like to be a little cautious.
Okay. I would like Professor Subhadeep Ghosh, our HOD, his department, to say a few words about this talk.
Yeah, thank you, Pankaj, and thank you, Sreerup, for being with us, for agreeing to give this wonderful talk, and thanks to Pankaj and Subhadeep in particular for making me agree for this HCM. And it was 175 people at one point, and till now about 70 people are there in this meeting, listening to the discussion, even after 2 hours. So that tells the intensity and the depth of the field. The best part of this kind of talk is that we often do not get to go to learn the making of a scientist or the philosophy, underlying philosophy that made them. So from that point of view, it was a wonderful talk. Particularly, there are many students who just joined in our institute. They were listening to this talk, and this chat box is actually overflowing. And there are people who also watch in the Facebook Live. So thanks a lot, and we hope that you will again with us, come back once again in another mesmerizing.
I'm sure, surely.
Thank you very much.
Okay. Thank you very much.
So with this, we are coming to the conclusion of the session, and really it was a wonderful moment for all of us. And Sreerup, thanks a lot from bottom of our heart to give us such a splendid lecture because it was beautiful, and I can see from the comments received by the student that they really enjoyed, and that's a thing that was the main motivation of bringing you here at this time, and it worked quite beautifully. And thanks a lot. And I would like to make an announcement that our next talk will be again one of the interesting topic, fluid turbulence, and given by another the well-known researcher of Indian science, Professor Jayant Bhattacharya. He is quite veteran in this field and gives the lecture at a very colloquial level. So please join us next Wednesday on 2nd of September at 4 o'clock for the next day's colloquium. So thank you all for such an active participation. Thank you, Sreerup, And thanks to our technical team, Basav, Hemanto, and others. And with this, we finally conclude the session. Thanks a lot.